Yeah, warm welcome to all of you for this event. We will talk a little bit about what Copenhagen Atomics is all about. As you know, we humans have been here on the planet for 100,000 years or something like that. But in the last 100 years, we invented more stuff than we did for the first 100,000 years. So like that's a little bit odd. Like why did we invent so much stuff just in 100 years when we didn't invent all of it? Is it because we became more intelligent or something? I don't know. I think it's because we got access to energy. That's the reason why we started invented all kinds of stuff, because before we had plenty of energy, we had to work in the field and basically make food, or at least 80% of the population had to work really, really hard to make food every day just to survive. But once we got energy, then we could concentrate on other things. And of course, this is also why we have this energy equals prosperity on our t-shirts, because we're a strong believer that it's important in a modern society to have energy at low cost and hopefully green. And then of course there's the reason I think why we're all here is because this crazy thing about thorium, that it was discovered in 1942 that you can get energy out of a material called thorium. And it turns out that a ball this size can generate all the energy you need for your entire life, not just at home, but also your share of the energy in society. And it only costs $100 to dig it out of the ground, so it's not very expensive. Of course, the obvious question is, so why are we not using it? Because we're actually not using thorium as an energy source today. If we look at, is there enough thorium on the planet? It turns out that 5% of global energy today comes from uranium-235, which is the type of uranium we use in nuclear reactors. And there's 1,000 times more thorium on this planet than there is uranium-235. So there's lots of thorium, and like I said, it's very cheap. So it's kind of crazy to us why we're not using it. We already learned in 1942 that we can use it. And of course, the reason why we're not using it is because we need some sort of machine that can extract the energy out of thorium. And that machine has never really been invented. There's been many attempts over the years, and people have tried to put thorium in all the classical nuclear reactors, but it doesn't work. And it's actually not very difficult to prove on a napkin that it will not work, because it's not that you cannot get any energy out of it, but you cannot get energy out of it efficiently so that it's cheaper than uranium, for example. And that's why all the people who've tried in the past to do it in classical reactors have ended up not having a commercial solution. But that's what Copenhagen Atomics is all about. We started this company because we want to make that machine. And the obvious question is, of course, so how far are you along that journey? And that's what we will talk about today. Our long-term goal for Copenhagen Atomics is that we want to mass manufacture these machines or reactors that can take energy out of thorium. And I will talk a little bit about today how it's done, but I will not get too technical. But maybe the questions, you're welcome to ask questions. Sort of what we're planning to do is build these reactors in a big box, and the box has roughly the same size as a 40-foot shipping container. And each of those boxes can generate 100 megawatt of thermal energy, which is roughly equivalent to 42 megawatts of electrical energy. But I think one of the things we should talk about today is how close are we actually to make it work, because so we already built a couple of these reactor prototypes in Copenhagen, and we've started testing them. In our current facility in Copenhagen, we're not allowed to make chain reactions. So we can only heat it up with electricity and pump these salts around and test that everything is working with thermal expansion and heat transfer and all these things. We've currently built 2 of these test reactors, and we are getting ready to build the third. The third should be ready next summer, something like that. And you know, this is a sort of a rough image of it. It's before it gets painted. And then the next step, after we have sort of made sure that it works in Copenhagen, is that then we made a collaboration agreement with PSI, where we can then put it on a truck, drive it down here, and then we can make some experiments where we can validate even further that it works. You could say we turn on the chain reactions, but it's done in a very scientific way, where it's a physics experiment to see, does it actually work exactly like the simulations? And that's the whole point of the experiment, is to compare a physical experiment with the simulations that we've done now for 10 years to make sure that we get the same results in the physical world and in the computer simulations. And once we know that hopefully they are the same or very close to each other, then we can be allowed to apply for licenses for commercial reactors, which is then a couple of years later. So what we plan to do is to build the reactor starting with the fuel and some of the parts in 2025. Then we will assemble the reactor prototype in 2026 and eventually load it onto trucks, drive it all the way through Germany. So, of course, one of the important things is to show that it works and that it has the same data as the simulations. But I think it's also important for the nuclear industry and the society at large to show that we can actually build something in one country, move it to another country, set it up fairly quickly, get it to work, take it down again and move it back. Because that's one of the problems with the nuclear industry today is the type of reactors that they're building in the UK, for example. It takes more than 10 years to build and, of course, extremely expensive. And I think that model has sort of come to an end stop. I think if we look ahead 10 or 20 years from now, I don't think we will be building reactors the way we used to, building these huge construction projects with 5,000 workers. But let's see, that's just my prediction. Then I want to talk a little bit about what are some of the steps that we need, some of the technologies that we need to develop before we can get to this. This is our target price in the long term. Our first commercial reactors will not end up at this price, but we believe that maybe in 2035, something like that, we would potentially be able to reach that price. And today, well, there's different prices in different nuclear power plants, but some of the nuclear power plants that have just been built, they have a price roughly around $100 per megawatt hour electric. So you can see if we could reach $20 in 10 years from now, that would be really awesome, right? But so what do we have to develop? What are the technologies that we need to prove before we can get there? So first of all, there's the problem of corrosion that is often mentioned with the molten salt reactors. We believe that we've solved that to a sufficient level where that's not what is stopping us from getting to this price. Of course, we still want to improve on corrosion, but it's already good enough to reach that price. Then we have developed this onion core, which some of you have heard about, where it's a new type of nuclear reactor core, which is very efficient. It has very small neutron leakage, and also is really, really good at converting the neutrons from the fission and capture the thorium in the blanket will capture those. I'll talk a little bit about that later, the onion core, but we've already developed that and patented that and done a lot of simulation on that. And then we need lithium-7. So when you dig lithium out of the ground from mining, it's a mix of lithium-6 and lithium-7. And in order to make these reactors get to these price levels over here, we need to have very, very pure lithium-7. And that's not available today in the industry. It has been done in lab scale, so we know it can be done. But of course, we need to scale it up and show that we can do it on industrial scale. And we're doing that right now in Copenhagen. We're not done, so that's why there's not a green check mark, but we're actually getting very close. So I think by 2026, we will have that completed. And then there are some of the next ones. We've already started working on the next ones, but they're not going to be completed before 2026, which is where we are supposed to have this first reactor test ready and ship it to Switzerland. So these next 4 steps, of course, is something that we need to work on in the future. Fuel transfer from the blank to the core, that basically means taking the uranium that is created in the blanket of the core and transfer that into the center region or the core region of the onion core. And then we need to remove fission products. The first experiment will already remove all the volatile fission products. That means all the gaseous, xenon, krypton, things like that. So this is already better than traditional reactors. All the traditional reactors we have around the world today do not remove fission products. And that's one of the reasons why they are super inefficient in the way they use the fuel. And that's also part of the reason why they're at this price point. But we will start working on that. We've already done some of it, but it will take many years. Honestly, it will take probably 10 years to develop this fission product removal in order to get all of them out of there. And then we need something like carbon composites for the core, probably silicon carbide, and we're already working on that, but getting new materials approved in the nuclear industry takes many years, so that's why it's sort of further out in the timeline, because even though we already started working on it, it will take many years before we will get all the approvals. And then, of course, mass manufacturing is important. And what we want to do is we want to set up an assembly line where we make these reactors in a factory. And we think of it a little bit like a car assembly line, where we want to make one reactor every day. Of course, you know, some of the car factories, they make thousands of cars every day. And there's actually less component in our reactor than there is in a modern car. And we only need to make one every day, so that shouldn't be too hard, right? But of course, in the nuclear industry, there's a lot of requirements towards quality assurance. So not only do we need an assembly line where people can put things together, we also need to make a lot of checks that everything is done correctly and according to specs. And we need to build that assembly line. That's very expensive and will take a number of years to build that. The total energy production of the planet over many hundreds of years, you can see that since we started inventing all this stuff, we have also started to use a lot more energy. But when you start to look at these numbers, you realize that it's mostly people in the rich part of the world. There's still 5 billion people who don't use a lot of energy, and they would really, really also like to have refrigerators and washing machines and air conditions and cars and airplanes and computers and all that stuff. So my thinking is that this chart will just continue to go up. If we can make enough energy for all those 5 billion people, then this will just continue to go up. And there's actually evidence that even people in the rich part of the world, they also want to use more energy. And you can see that most of this energy comes from coal and oil and gas. And there's, of course, debate going on in TV and other places saying that we should stop using coal and oil and gas. That's going to be super difficult if we don't invent something new. I do applaud that these 22 countries, they want to triple nuclear, so they want to make that 3 times bigger. But that doesn't really cut it, right? We need something more than that. And I also know that wind and solar people, they also want to do something. But we need something that has a much bigger potential. And I hope that what we provide could potentially be that thing. This is all energy, including heating and all the energy for making steel and cement and all these things, transportation. Here we only look at electricity. Electricity is roughly 20% of the chart we saw before. So electricity is a small percentage of the global energy, but of course, very interesting for nuclear energy. And again, you can see that most of this is made from coal and gas. Actually, more than half is coal and gas. And wind and solar has grown a lot in the last decade. You can also see, if you look at the slope here of how quickly it's growing, you can sort of calculate how much new installation capacity we have in the whole world every year. You can also see that the value of this market, so when we sell all this electricity, it costs roughly $4.5 trillion US. And back to this, if we calculate the slope, we install roughly 75 gigawatts of new capacity every year around the world. If that were to come from nuclear reactors from Copenhagen Atomics, all of it. Of course, this is a sort of wishful thinking, but if we built 5 reactors every day, we could deliver all of this growth in the electricity industry or electricity sector all over the world. But of course, that's not possible. I mean, different countries want to use their own solution, and the people who build coal and gas, they probably also want a cut of that market. But with all these things that, AI and electrical vehicles and power to X, where we try to make different types of fuels from electricity, we believe that the global electricity market is going to really grow, maybe even triple before 2050. This is really wishful thinking. I think there's a lot of people out there that said, this could be great, but there's no way we can do that with wind and solar. And if we at the same time also have people who want to cut back on gas and oil and coal, how are we gonna do that? And of course, this is where we see an opportunity, actually a really big opportunity. The rough market size of that is $10 trillion per year when you get out here when it's actually been installed. So it's a lot of money. But then in addition to that, there's actually other markets. We talked about electricity is only 20% of the global energy consumption. But there's also all the other things that we use energy for. And one of the things that is super important, at least to me, is when you go down to your local supermarket and wants to buy food and you look at all the food on the shelves, I don't think many of you realize that half of the energy in all that food comes from natural gas because it's fertilizer. And most of that fertilizer is ammonia. So we have huge ammonia plants around the world, and they produce ammonia and they put it on the fields and different types of fertilizers. And then we grow the crops and then we make food for either the cows or even bread for ourselves. And so when we eat the food, half of that is natural gas today. And that's rather important because all of us need food. The people say, no, we should just stop using natural gas. Okay, then they need to explain then how do we make the food without natural gas. And of course, we can make ammonia from electricity, but today it's super expensive. It's typically 3 or 4 times more expensive with what is called green ammonia than traditional gray ammonia, which is made from natural gas. And today, this is the global ammonia market. So today it's roughly around 200 million tons of ammonia per year. But a lot of people expect that to triple before 2050. To triple that, if we assume that all this new ammonia was to come from electricity, then we need 600 gigawatts, I actually think I have. Yeah, 600 gigawatts of electricity just to make that new ammonia. And that is actually twice the size of the entire European electricity grid. And actually, the reason why they think this will go up to 600 million tons per year is because it's not only meant to be used for food, it will also be used for refrigeration. And then finally, a lot of the big ships, ocean-going ships, are also meant to change away from diesel oil and heavy fuel oil and start to sail using ammonia. So that's why the ammonia market will grow really explosive way the next years. And so Copenhagen Atomics, being from Copenhagen, we work with Topsøe. Topsøe is the main company or the biggest company in the world supplying these ammonia plants. And they are also located in Copenhagen. But they also recognize that now we need to start making ammonia from electricity. So they have made these new things that can generate hydrogen from seawater, basically. And with that hydrogen, you can make ammonia. And then when you burn ammonia, it actually just creates water and CO2. Nitrogen. So no CO2. And that's, of course, the beautiful thing about ammonia is that it has no greenhouse gases associated with it when it's green, when it's made from electricity. So this is one of the things that we have high hopes that we can work with Topsøe, and together with them we can install a huge number of ammonia plants around the world to make all this new ammonia that we need, but also make all the food we eat more green. And that opportunity is a much bigger opportunity than if we as a company were able to get the entire European electricity market, not only the new build, but the entire electricity market in Europe, which is of course, not possible. So this is a big opportunity for us to work with them. Then my final part of the talk is about some of the achievements that we've made. And then after that, I will open up for questions. Right now in our facility in Copenhagen, we have 11,000 square meters, roughly, 75 employees. Here are the 4 founders who started the company. We were 3 engineers and 1 physicist who started the company. Over here are some of the companies that we are working with. Many of these we have sold technology to because we are not only making nuclear reactors, we are also developing the molten salt reactor technology or molten salt technologies. And a lot of these universities and national labs, over here, they have been buying our technology, and we help them do research in this field. Here's some pictures from our facility. We moved in this new facility last year in the fall last year. These tanks are for salt production. We're the only company in the world that makes these fluorine salts in ton scale. There's no one else anywhere that makes these fluoride salt at this big scale for nuclear. And we've also set up our own pump production. And the unique thing about this pump, so this one is the one that we now manufacture in sort of a production quality. We manufacture this in batches of 50, so it's not a giant production, but still. And this part here is an electrical motor that runs at 700 degrees. So it's red hot when it's running, and it's actually really beautiful to look at. And nobody else anywhere in the world has an electrical motor that can run at 700 degrees. Yeah, so we're kind of proud of that. We also make these test systems, which we call loops, and we sell those to universities and national labs around the world to help them also do research. We found out that it's roughly 100 times less expensive to find an error or bug in our components on these systems than when we put the components into our test reactors. So it's really, really, really important for us to run a lot of tests on these to find all the errors or bugs that needs to be fixed before we put it into a reactor, because it's a lot less expensive. And we also have the biggest test capacity in the whole world. We're not entirely sure, but we believe that we have more test capacity in Copenhagen than all the other people in the entire world that are doing research in molten salt for nuclear. So it's and actually now we're starting to do testing services. So also other companies or other universities, they can come to us and run the tests at our facility, because sometimes they don't have the capabilities of running these tests at their own labs, especially if it's tests with uranium and thorium bearing salts. And of course, here are some of the pictures of the onion core, which we are really proud of, because that's the reason why the company exists. This is the reason why we believe that we can make electricity or energy at a much lower cost than any other form of energy. And it's roughly 2.5 meters in diameter. This is a picture taken from above, and you can also see all the different, here are some pumps and all the different pipes inside one of the test reactors. And then, yeah, the reactor we're working on. So that concludes my talk.